Hey, Samaya. Hi, Alton. Let's see. While we wait for more students to join us, please go ahead and write down and answer the do now. Wow. A do now. I know. All right, so we have a do now on the board. Okay. Hey, Esther. Hey, Laviva. Good morning. Happy Monday. Oof. Hey, Isabel. Hey, Justin. Hey, Rosie. So while we wait for everyone, let's go and let's start the do now. I hope you have your notes. Hope you can write that down. We're starting a whole new unit today. It's waves. Get excited. Hello, Aaron. Hey, Meg. Alexi Aminev, finally using your Bronx Science account. Hello. It's good to see you. All right, so let's get started on the do now, right? Let's start. I want to start the stream at around 11:35, so that gives the rest of you 3 minutes to complete this do now. So give 2 examples of waves you're familiar with, or a wave you're familiar with. Like when people say, "Oh, look, there's a wave," right? Like what are they really talking about? It is a thing, right? It's a thing that can be described. Good morning, Bruno. Hello. Good to see you. Good morning, Lars, Ethan, Ali, Timothy, Justin, Rosie. Hello, hello, hello. So good to see you. We have 2 minutes left. We're going to start at 11:35. So let's get started on the do now. 2 examples of waves. Where have you heard it in writing? Where have you read about it in books? Where have you heard about it in videos? Where have you heard it in everyday speech? Oh, cut myself. Interesting. The Sound of Music song about Maria. Um, could you be more specific about that, Josephine? I'm not familiar with that song. All I know is I'm 16 going on 17, and these are a few of my favorite things. And Edelweiss und Auf Wiedersehen, good night. And the actual Sound of Music song. How do you? I don't know that, Aiden. I wish we were in a Zoom meeting, then you could sing it for us. Um, Timothy, that's a really great question. But it's now 11:35. Well, it will be in 5 seconds. So way to go. Let's type your answers in the chat. Okay, I want to see 100% participation in the chat. I want to get as many examples as possible, and hopefully you guys all have a different answers, right? So let's put them out there. Even if you only have one example, please put it down. I just want to see how you think. So we have light, sound, we have radio waves, we have sound waves, ocean waves, light and sound, light. How do you catch a moonbeam in your hand? Sound, radio, sonic waves, light waves, sound. Lara, good morning. I haven't seen you in forever. Girl? Hair waves. Thank you, Bruno. And Tim also mentioned the stadium waves, right? Where everyone just kind of goes up and down, right? Microwaves. I'm very surprised only one person has said ocean waves, okay? Arm waves. Is that also light? Yes. Okay. Isabel, what do you have to say? Don't tell me you just said hi, Mr. So, and left. Rosie, still waiting for your response, young lady. Okay. So light. So even though it doesn't really sound like it, it's okay, Isabel. I don't care, right? I just want to see everyone putting down something. Because guess what? Most of what you guys all put are all the same. So let me give you an example. Light, radio waves, microwaves, electromagnetic spectrum waves, X-rays, they're all the same thing. They're all different forms of light. Hey, Gallagher. All right. I really want to focus on the waves that you can see, right? Yeah, and not in terms of light waves. I want to talk about the waves that you can actually see moving, right? And let's get into Bruno's example, which is not a real example of a physics wave, but I wanna start that as the jumping point of our discussion. Hair waves. All right, Isabel, where's Naya? Where's everyone else in your group? All right, and that goes to all of you as well, right? This is a little lower than what we're used to, around 24. We're usually around 34, right? So get your group members' butts in here, text them and be like, yo, you're missing the live stream. It's lit today. Excuse me. It's lit every day. So hair waves aren't what we typically in physics call like real physical waves. But why are they called waves? Can someone answer that in the chat? What about hair waves makes us call them wavy, right? Or like waves? Isabel, what's IG? What's IG stand for? It's not Instagram. I guess. Oh, thank you. Thank you very much. Thank you, everybody. Because of their shape, right? How are hair waves shaped? Like that, right? And that's the kind of that's the shape that most physical waves will take. It's not necessarily like every wave is going to look like this, but most waves you can approximate as a sinusoidal or cosine, which is sinusoidal, right? Curve. And the only difference between this wave and like an actual real wave is that waves move, right? So like the reason why a hair wave isn't a real wave is because it doesn't move. It just kind of stays, right? So it needs to be moving in either this direction or this direction. So like these peaks need to be moving there or these peaks need to be moving there, right? So here's an example. And when I'm talking about waves we can see, I'm talking about waves where we can see these peaks move, right? Those are going to be known as mechanical waves. All right, here's my best example at home that I can create for you of a mechanical wave. All right, I have a very long cable here, and it's from my headphones. Right? Why are they so long? Because these are the same types of headphones you use in like a music studio, and for that kind of stuff, you need to really walk around a lot. And yeah, it's useful if these are super long. Okay, so here we go. I'm gonna move my arm up and down just once, and hopefully we'll see something. Whoa, look at that, all right? Whoa, so if you see that I created a little hump, and that hump kind of just traveled all the way down there, right? If I create two, if I go like up and down twice, I'll get like these two things, and then they'll be moving this way. Okay, it's a little hard to do here. Yeah, I mean it moved this way, and then it moved back. The reason why it moved back is it's attached to something on the other. It's attached to my headphones on the other side, and when the wave hits it, it kind of reflects back, and that's why it kind of comes back. All right, that's not really important. What is important though is what you just saw. It's an example of a mechanical wave. And I want to define what a wave is. Like a wave, all a wave is the transfer of energy. Spatial. It's the spatial transfer of energy or movement of energy. All right. So if I have some energy at point A and point B has no energy, all I have to do is send a wave from point A to point B and I move the energy. What type of energy was moving here, right? I mean, like, as soon as I move my arm, right, my own chemical potential energy stored like as the food that I eat. Meg, I know you'll like this. I made BA's best chocolate chip cookies. They really are the best chocolate chip cookies I've ever had. The browned butter changes everything. Anyway, what's up? That's like 50 calories. That's like 20,000 joules. So I just ate 20,000 joules. Okay. When I move my arm, right, I'm gonna burn probably around 1,000 joules, right? So boom, right? I lost that energy, right? I lost that energy. Where did it go? Energy is always conserved, right? So if I lose some chemical potential energy just by moving this, right? Where does it go? Some of it went into heat, right? That's why when you work out a lot, you get really hot, right? And your armpits get really sweaty, gross, okay? It's not a pleasant noise, is it? Okay, right? So some of it turns into heat, but a lot of it's going to turn into kinetic energy, right? What type of kinetic energy, right? Whose kinetic energy? Well, my own kinetic energy, right? Like my hand is moving, right? But also the molecules in this cord are now moving, right? And guess what? At one point in time, the molecules on this side were not moving, and the molecules on this side were. So these had kinetic energy, these didn't, right? But when I move it like that, then these molecules can get kinetic energy, right? And when the pulse is done moving, right? So as it moves this way, right? I would say initially these molecules have kinetic energy, but after the pulse has traveled through, this section of the wire doesn't have any more kinetic energy. Where did it go? It all went to that side, right? So that's why I call waves a transfer of energy. And when you see this kind of motion, when the peaks are moving, that's actually physical bits of kinetic energy and units of kinetic energy that you can see. So whereas before we said energy is invisible, right? It's just a super weird, nebulous, invisible quantity that's always conserved. Like, I know why it's useful, right? If I know how much something has fallen, I can calculate its speed, right? If I know like the electric potential it has traveled through and its charge, then I know how much its potential energy has changed, and I can then know how much its kinetic energy has changed, right? If I compress a spring a certain amount, I know how much energy is stored in the spring, and when I let it go, I can calculate how fast the thing is after it's launched from the spring without even ever looking at forces, right? That's why energy is useful, but it's still super weird because it's like this invisible thing. Finally, with mechanical waves, we can actually kind of see like the physical manifestation of a lot of energy, right? So what makes waves, some waves carry a lot of energy and some waves carry a little energy, just by looking at them, it's usually the height, right? The height of the wave corresponds to how much energy is being driven, right? So like, obviously my wave that I sent through my little cord doesn't have a lot of energy. I only shook my hand that much. What if I shook my hand that much? Then there's going to be like this huge wave like traveling through the thing, and there's a lot of energy. If you want to bring the analogy back to ocean waves, if you have like a really shallow ocean wave, that doesn't carry a lot of energy. When it hits you, you're like, oh, I'm not scared. Oh, it's splashing on me. Ah, tee tee. Hey, Naya. Okay. Echolocation waves, Rosie, is another form of sound waves. All right. Naya, the brown butter is butter that you cook in a. If you've ever cooked in a pan, right, and you put butter in the pan, and your pan's too hot, your butter burns, right? Which is why a lot of recipes that call for a high heat but still like the flavor of butter will ask you to put butter and then immediately mix in some cooking oil. So it's like half olive oil, half butter, and that raises the burning point of the butter. But brown butter is like you're burning butter on purpose, and it gives it like this toasty, nutty, caramely kind of taste. But you do it over very low heat, and it's a pretty slow process. It takes like 5 minutes. Yeah, so you're kind of browning the butter on purpose. Whoa. Okay. You distracted me, Naya. Naya, I'll link you the recipe. These are the best cookies I've ever had. Huh. The key when you make the brown butter, you should have like a silicone spatula or a wooden spoon, something that's kind of soft. You should be constantly scraping the bottom of your saucepan in which the butter is in, because you don't want it to burn, right? So you want to keep on mixing it. You don't want the bottom butter only to be getting super hot and the top butter kind of like just chilling. You want to be mixing it up the whole time, scraping it. Otherwise, you're gonna have like black bits on the bottom. And what you want is brown bits. Okay? No, these take. I made them in like an hour. Okay, so let's keep going with waves. Okay. Obviously, like in an ocean wave, like if it's a shallow wave, oh, tee tee, this is fun. Social distancing. Okay, please stay one wave away from me. But for like a kind of on a sadder note, if it's like a natural disaster and we're talking like a tsunami, right? If it's like a super tall wave, obviously that wave has a lot of energy, and it has enough kinetic energy to destroy buildings and stuff. Where did that energy come from? It came from over 2,000 miles away, right? In a fault in the earth. And like when that fault like moved, boom, right? Like these two tectonic plates, they move. That's so much energy being released right there. And that's a lot of kinetic energy. You got to think it's not even kilograms, right? It's like 10 to the 8 kilograms of mass, right? This is like the actual Earth, right? Moving around like 5 meters in like a microsecond, right? These tectonic plates, they have so much tension, and then all of a sudden, boom, they just shift, right? That's so much kinetic energy. The water absorbs all that kinetic energy, and through the mechanism of a wave, it reaches the shores of really unfortunate coastline populations, right? So that's an example of a very high energy mechanical wave, right? A wave that transfers a ton of energy rather than just the trivial amount of energy I'm using with my hand and like putting over there. Okay. Let's say you have the same level of magnitude in one wave. I don't want to go over frequency and stuff yet. Okay. We will. I want to go over basic properties of a wave, okay? So the number one important axiom to remember about mechanical waves is it requires a medium. Through which to travel. And this medium is frequently used to define or identify the kind of wave it is, right? So a water wave, the medium through which it travels is water. A sound wave can travel through air, that's the medium, or it can travel through water, or it can even travel through solids, okay? The wave I just showed you right now in our video lecture was just a wave traveling through a cord. The cord is the medium. The medium is just the material through which the wave propagates. And propagate is another word for travels, right? All mechanical waves require a medium through which to travel. Which is why every sci-fi movie you've ever seen where there's like explosions and like sounds of the explosions, like lasers, like pew pew, totally fake, because sound needs some medium through which to travel, and in the vacuum of space it won't travel because there's no medium. Whoa. Okay. Now what about electromagnetic waves and radiation and light? They can travel through a vacuum, yes, because they are not mechanical waves. The thing that makes light waves so special is that it doesn't require a medium through which to travel. And we're going to get there in a little bit, okay? And by a little bit, I mean like next week. Because this week is going to be focused on mechanical waves, and then next week we can focus on other waves. All right, so get excited. All right, so they need a medium through which to travel. This medium affects speed, the propagation speed. V, okay? This is the only thing that affects the speed of a wave. It's not how hard I shake it, all right? if I did an experiment, okay, and I shook this like this or like that, no matter how hard I shake it, the pulse is going to travel the same amount. How hard I shake it, that is a quantity we call the amplitude, right? This is the size of the wave. The other thing we can talk about, and it's been referred to by Alexei, is frequency. This is how many pulses per second, right? This is cycles per second. And that's related to period, t, where t is just 1 over frequency, or frequency is 1 over the period. This is a formula you should know from math class, but we're going to be using it a lot here, okay? Okay, moving on. Let's get to the nitty-gritty today, all right? We're going to learn one really important formula. But first, I want to talk about the anatomy of the wave, all right? This is very related to math class. Let's pretend that this is like a cross-section of water, right? So I'm like, basically, what am I doing? I'm like swimming and I'm looking at the water this way, okay? So this is a cross section. These waves are traveling in this direction, okay? Okay, so if I want to identify the amplitude, it's always the, okay, so first of all, I want to take a step back from the thingy thing. All right, the amplitude is the maximum displacement you'll ever feel from equilibrium, right? So this is amplitude, not this, it's this, okay? This is something known as a crest, like the crest of a wave. This is a part we call the trough, and it's spelled super weird, T-R-O-U-G-H, okay? I know, it's pretty weird, okay? And there is one more thing that we like to call, and it's called the length of the actual wave. It's like the physical length, okay? So we're going to call that the wavelength. It is represented by this Greek letter, lambda, which is the Greek L, which is why we use it for length, right? So this is wavelength. And wavelength is defined as the length between two identical parts of the wave, right? So I can go from trough to trough. I can go from crest to crest. This is also 1 lambda. I can go from an equilibrium point to an equilibrium point as long as they're both going down. I don't want to take an equilibrium point going up, right? So this is also a lambda, right? These are all the same. That is the length of the wave. So I either go from trough to trough, crest to crest, midpoint to in phase midpoint, okay? If you really want to get funky, you can go from here to here. Well, why would you do that, right? I mean, like, don't do that, okay? Okay, so going back to like a very basic thing about waves is it needs a medium through which to travel, but the only thing that is ultimately displaced is energy. What does that mean? The only thing that's displaced after everything is moved is energy. So as this wave moves, energy moved from this point to this point. Every molecule in this wave did not move side to side. All they did was move up and down, and they eventually returned to the same position. So basically, if I have a rubber duck here, okay? If I have a rubber duck here, it'll go down, right? Because this trough is going to hit it, right? This rubber duck will go down, up, and then back down, but it will have never moved side to side. The actual medium, the molecules of the medium, don't experience a displacement after the wave is done traveling. The only thing that is displaced is the actual energy. That's the thing that's moving, okay? So another way of defining amplitude, right, is to not look at it just by looking at the wave. You can think about it as if from the point of view of a water molecule, right? What is the amplitude? That water molecule will tell you the amplitude is, it's the largest height I experienced from my starting point. It's the most I was ever displaced from my equilibrium point, right? So let's, for example, look at this molecule, right? It's probably like a meter above the equilibrium point, but a couple seconds later, it'll probably be when the wave is now in this position. Right, because the wave's moving this way, right? I'm going to show that wave in green. If I can find my markers, right? All right. The green wave represents my wave at like a split second later, right? Then this molecule that we're focusing on, that I'll represent with the color purple, okay? This molecule is now up here, right? Right? So, and then it'll eventually come back down, right? Like, I'm going to draw a wave with orange. Like when the wave's all the way over here, right? By the time it's in this position, right? Then the particle's back home. It's back to where it usually was, okay? And its displacement from equilibrium is 0. But at the green time, that single molecule is the highest it's ever going to be. It's like, whoa, dude. Like if you're thinking about like the stadium wave where everyone does this, that molecule at the green time is like if the one person is like this, right? And everyone around him is like a little lower, right? All right, Mr. So, I heard from one kid that any object that has 3 dimensions of movement will move in. Yes. Well, actually, what you have to remember about that is when 0 counts as a value. So this purple particle all it really has is y velocity. Does that mean it doesn't have x and z velocity? It does, but the x velocity is constantly 0 because it's never moving side to side. Its z velocity is also 0. It's never moving in or out of the page. It's only moving up and down. So it has x, y, and z velocity, but only its y velocity is ever non-zero. Okay. That's it. All right. That concludes our lecture. I'm going to send a practice sheet out by 2 o'clock. That'll be due by tomorrow morning at 11 a.m. I really have to say, I changed my mind because I really want you to understand this first. We're going to learn the formula Wednesday. Yeah. Well, this has only really been going on for 30 minutes. No, I wanna keep it like this. I wanna go over like really basic stuff about the wave first, and go from there. Okay, so we are gonna learn like the most critical formula for waves Wednesday, but here this little bit, I'm gonna timestamp this. Right, this is called like motion of a single particle in the medium as a wave travels through it. That's the part we should really be focusing on for the homework, right? It's due tomorrow at 11 a.m. But with respect to that, I'd like to really address really quickly before we go the assignment for last week. I kept it light so those of us who are already a little behind could catch up with their work and stuff. But I have to, I'm just a little disappointed. And I know it's not a lot of you in the chat, but I had so many turned in at midnight yesterday, 5 minutes past midnight yesterday, an hour past midnight yesterday, some this morning. It's so last minute. And then a common theme I heard was, Mr. So, I really didn't understand this unit. I'm sorry, blah, blah, blah. And that's fine. Thank you very much for being honest with me. But why are you telling me this at the end of week 4? Like that in itself is the real problem, right? I get that it's hard to understand and it's, it's not easy. And if you don't understand magnetism, that's perfectly normal. But you didn't have to put yourself in that situation, right? If you asked a question anytime between week 1 and week 4 and not just at the end, like I just don't think that's a good attitude. All right. Just moving forward. Okay. Some of you who have even done that are the same ones asking me for raves and recs. Like, how am I supposed to write a good rave or rec when I don't hear from you for a whole month until like the last big thing is due, and then all you say is, I don't get it. Like, that's not the academic attitude I'm kind of looking for. To end things on a positive note, get pumped because this unit is kind of fun, and it leads to light, which is really exciting. And it's a lot more exciting than magnetism. So hopefully we won't even have this problem for future units. See you guys.